All right, so let's first talk about the lottery. Okay, so again, I'm not advocating to play the lottery. I think it's a bad idea. I think it's also bad that the government sponsors it because, you know, the government's another way they're trying to get tax out of you for one thing. But let's go ahead and pretend you decide to play and you win. You win the Powerball, say, and they give you a choice that we're going to compare. You can either get $1 million starting right now. To keep it simple, say once a year, every year for the rest of your life. So that's option one. $1 million starting now, every year for the rest of your life until you die. And by the way, I actually don't know for sure if this is true, but I think it's probably true. Somebody could look into it. I think they don't let you pass it on to your descendants, right? After you die, I don't think they let you pass on the lottery winnings. That would be unlikely for them to do that. So it's every year and from now until you die. So that's one option. Second option is they give you a lump sum right now and then nothing else. Say $10 million right now. Question is, which is better? Which one should you choose? Which is better? And I hope it's pretty obvious that the answer depends. What does it depend on? Well, for one thing, how long you're going to live. It depends. On what? One thing it depends on, I'll call it A, is how long will you live? If you know you have a terminal disease and you're probably going to die in the next year or two, take the $10 million right now. On the other hand, if you feel really healthy, you're pretty young, you know, you're about 20 years old, say, like you probably are, and you think, oh, there's no reason I shouldn't live to be 100. Sounds like that might be the better choice, the $1 million every year for the rest of your life. On the other hand, is it really the better choice? You could take this $10 million right now and invest it if you've got the discipline to invest it. So maybe this is still better. And so another thing it depends on is not just on how long you live, but what kind of investment returns are available to you. What investments and what kind of return are you going to get on those investments are available? Yeah, what are interest rates? So if the interest rate is really, really high, 10, 20, 30%, if you could somehow get such a thing and it was guaranteed, $10 million right now sounds pretty good because you could invest it. If you invest money at 30% interest rate, of course, that doesn't really happen. But if you did, just to pretend, for even 10 years, it would grow by a factor of almost 14. So in 10 years, it would grow from 10 million to 140 million almost, if you could get a 30% interest rate. Over 20 years, it would grow by a factor of 190, from 10 million to 1.9 billion. Of course, nobody gets 30% interest rates. And even if you could get a 10 or 20, 30% interest rate, typically the investments are more like stocks when you're doing that, and it's more volatile. Or Bitcoin, whatever, you know, digital currency. Yeah, it goes up pretty fast, but it can also go down pretty fast. So it's more volatile, it's more risky. On the other hand, if your investment returns are pretty small, 1, 2, 3%, then that's not going to grow very much, and this sounds better again. How can we mathematically analyze this? Our procedure is, or the procedure that many people use, is to compare the present values, partially because the $10 million right now is its own present value. And so you really only have to think about this one. Compare present values at whatever interest rate you're assuming? The answer is going to depend on the interest rate. Now, again, real life is more complicated than our simplified models. Nobody really knows what stocks are going to do in the coming 10 years. Nobody really even knows what bonds are going to do, and bonds are considered safer. But things are kind of crazy right now here in 2022, as you know. Inflation's going on. What's going to happen? It's not really very clear. However, even if you think about individual interest rates like 6% or 8% or 10%, it's still a worthwhile exercise to do because it kind of gives you windows for comparison. And you might wonder sort of what's the boundary interest rate at which these are equivalent even. You might wonder that. So what is the present value? Again, the present value of option 2 is itself. What's the present value of option 1? This income stream, discrete income stream, which I should also tell you is also called an annuity. An annuity is anytime you got a series of payments. Let me go ahead and call it an annuity here. What's the present value of the annuity, which again really is the same thing as the income stream? Annuities don't have to be income streams. They could be payment streams that you are paying, like your monthly mortgage bill or something. What's that present value? It depends on the interest rate. Let's keep the interest rate unspecified until the end. Let's say R is the effective annual interest rate. I know the textbook problems back in chapter 8 typically did continuous interest rates, so you could use E, and so that made the integrals easier to do. But I'm also telling you, as I did last week, I think a week ago, you should be able to handle the effective annual interest rates too, where you do not use E. And before we write down the formula for it, let's think about it visually with a timeline. I'll make it down here. So here's the present, time 0. The annuity, you're going to get $1 million every year starting right now. So I'm going to draw a 1 there, meaning $1 million at time 0. At time 1, 1 year from now, put another 1. At time 2, 2 years from now, put another 1. At time 3, 3 years from now, put another 1, etc. I'm assuming you will live that long at least. How far do you go? Well, you don't know how long you're going to live. But let's just pretend we have n payments of 1, meaning $1 million each. If I have n payments and the first one starts at time 0, that must mean this is time n minus 1. And this is going to be your last payment. And what that is meaning is you are dying between time n minus 1 and time n. You die in here. Sorry to talk about dying. Die in here. In that year somewhere. Right? We're assuming the payments don't keep going. They don't go on to your descendants or any relatives or any friends for that matter. So you have n payments. What's the present value of all those put together? I have to find the present value of each one and add them up. First payment at time 0 is its own present value because it's already at time 0. Second payment at time 1, its present value I need to divide by 1 plus r, which is, yes, the same as multiplying by 1 plus r to the negative 1 power. But let me write it as a fraction. Third payment at time 2 has to go back in time 2 years to the present. So I got to divide by 1 plus r twice. In other words, do 1 over 1 plus r squared. Keep going until the last payment at time n minus 1. That has to go back in time n minus 1 years. So I do 1 over 1 plus r to the n minus 1. And yes, by the way, just for emphasis, this is the same as the entire fraction 1 over 1 plus r quantity squared, etc. This is the same as 1 over 1 plus r, the entire fraction quantity to the n minus 1 power, because 1 to any power is 1. And also, any fraction to a power can be computed by taking both the top and the bottom to that same power and making a new fraction. I hope you're at the point now where you can look at that and say, yeah, that looks like a geometric series. You see it? This is the AA, right? There's the leading term. What's the common ratio? Yep, 1 over 1 plus r. The common ratio, which our book calls x, but many books call r for ratio. Well, we're already using an r, is 1 over 1 plus r. For us, r is the effective annual interest rate. And the number of terms is n. N is the number of terms. So using the formula that I hope you maybe even have memorized by now, even though you can put it on your note card, right? Striving to do exams without note cards is better for you. The note card's just there for your security, to make you less anxious, I hope. The formula is a times 1 minus x to the n divided by 1 minus x, if x is not equal to 1. And if r is positive, then certainly x is not equal to 1. R is positive here, so in fact, x is less than 1, not equal to 1. All right, plug everything in. A is 1. 1 over 1 plus r to the n, I can write as 1 over 1 plus r to the n over 1 minus x is 1 over 1 minus 1 over 1 plus r. And that's a fine way to leave the answer. I mean, I could get rid of the 1 times in front there, like this. Some people don't like fractions within fractions. Well, that can be taken care of. You could either subtract the fractions in both the top and the bottom, and then when you do the overall division, multiply by the reciprocal. It's a little quicker to multiply the top and the bottom by the highest power there, 1 plus r to the n. If I do it to the top, to cancel on top, I've got to do it to the bottom so that I don't change the numerical value of the fraction. And if I use the distributive property to distribute that through the parentheses in both the top and the bottom, I do get some partial cancellation. 1 plus r to the n times 1 is 1 plus r to the n. 1 plus r to the n times this fraction, the 1 plus r to the n is completely canceled, leaving me with a 1. On the bottom, I don't get complete cancellation. I get partial cancellation. I get 1 plus r to the n minus these two things right there, partially cancel to leave 1 plus r to the n minus 1. That's not a ton simpler. You might even say it's more complicated looking, but at least there's not fractions within fractions there. But there is a problem here. We don't know what r is. We don't know what n is. That's where technology can come to help. Let's go ahead and use the spreadsheet again. So let's put the annual interest rate in cell B1. We'll just start with 10%, which is 0.1. Let's put the value of n in cell B2. You're 20 years old or so. You know, technology, medicine's improving. You very well may live to be 100. Let's say you assume you live another 80 years. I'm going to make a table of all the payments down here with the copy and pasting of formulas, but I also could just find the answer with the formula that's right here. However, if I do so, excuse me, it's a little tricky. I got to be really careful with parentheses. I'm dividing the entire top by the entire bottom. So I need parentheses around both just to play it safe at least. Yeah, for sure. I also need parentheses for each 1 plus R. R is in cell B1. By using a formula like that, it's going to give me flexibility to make changes. That's the great thing about spreadsheets here, is to make that flexibility to make changes. And I don't have to worry about dollar signs because I'm not going to copy and paste this formula. I don't need absolute cell references. To the n power, n is in cell B2, minus 1, all divided by, keep using parentheses, 1 plus R to the n power. I could put parentheses around those B2s that you see there. You don't need to. Order of operations would say to make sure you do the exponentiation before the subtractions. But in the next thing, since I have n minus 1 power, I will need parentheses. B2 minus 1. I've closed off all my parentheses. I am using this formula now, and I'm also using it in such a way that I can make changes to R and N and just see what happens. What kind of answer should I expect? Well, remember, all your payments are $1 million. In units of millions of dollars, they're all ones. There's 80 of them here if you pretend n is 80, starting at time 0, ending at time 79. These are present values. Present values are smaller than the actual monetary amounts. Because what does present value represent? It represents the amount you need now to invest, to grow to those later amounts. So the present amounts are smaller. We should expect an answer less than 80. How much less is not clear, but it should be less than 80. 10.995, effectively $11 million, is the present value of 80 payments starting at time 0 through time 79 if you assume the interest rate's 10%. Doesn't seem like very much, although it is somewhat comparable to the lump sum present value, which is itself, because it's right now. It's a little bit bigger, about $1 million bigger. So if the interest rate's 10%, and if you are confident you're going to live close to 80 years, it's better to go with that. But remember what I said at the start of this problem, if the interest rate's really high, 20, 30%, probably that's better. If I increase this interest rate from 10% to, for example, 20%, probably the lump sum's better, which means the annuity present value should be what? Should it go up or down? Should go down. It does, $6 million. Because the interest rate's better, you don't need as much money right now to grow to an equivalent amount in the future. There are things that I'm throwing under the rug here. I'm throwing under the rug the volatility. I'm throwing under the rug, like, maybe you want to invest even these things. Just kind of shoving it under the rug. I'm ignoring any amount of money you want to spend in either case. Although investing these things, maybe you don't get anything better, right? You don't necessarily get a better interest rate. There are complicating factors, like what's going to happen to interest rates in the future. Let's go back to 10%. What if I make the n smaller? Say 40 instead of 80. The present value should be smaller, right? Because there's fewer payments. Is it a ton smaller? Ready? I'm about to hit enter. Look at the present value. It's about $11 million right now. If I change n from 80 to 40, it goes down to Well, it went down barely. What? What happened? You're living to just 60 now instead of 100. The present value barely went down. Is that right? It actually is right, because the present values of those payments more than 40 years from now are very small, because 40 years and longer is a long time. It only goes down significantly once n gets significantly low, like say 10 or 5 or 4. Then it's going down more significantly. This is hinting at the fact that maybe it would be simpler to think about what happens as n goes to infinity. That might be a simpler approach if you know you're going to live a long time, because there's not much difference between the present value when n is 80 or when n is 70 or 79, 70 or 60. There's not much difference in value, so it might be simpler just to let n go to infinity. And you might say that's a key application of infinite series, is to just go ahead and let n go to infinity. Pretend you're adding up infinitely many things. It makes things simpler, even though you're not literally adding up infinitely many things. Let's also confirm the answer. Oh, let's do a smaller value then, like 40, with copying and pasting of formulas. We'll put the time here. We'll keep adding 1 to it, like we've done before, equals A5 plus 1. Click and drag that down until we get to 40, which will be what, in row 45. There we're out to time 40. The payments are all 1. I can just copy and paste that thing down by itself without adding 1 to it. Oops, keep typing the wrong thing. Equals B5 without doing plus 1. We'll carry all those 1s down. I could also have it up here, the amount that I'm depositing or receiving, I should say, and use a fixed absolute cell reference with $signs. What are the present values? In each case, I have to go back to this kind of expression, 1 over 1 plus r to some power, or if you prefer 1 plus r to some negative power. This is also the same as 1 plus r to the negative 2, for example. So I'm taking 1 plus r and raising it to the negative power of the number of years it needs to go back to time 0. The first payment at time 0 is already at time 0. Oh, I forgot, by the way, when n is 40, the last payment's going to be at time 39, not time 40. Get rid of that one. This one's already at time 0, so just do equals B5. Okay, with this one, it's equals B6 times 1 plus r. Here I do need both parentheses and a $sign to keep the cell reference fixed. Absolute cell reference, so there's a copy and paste. It's always a B1. The B6 doesn't really matter because they're all 1s, but I'll put it in there like that anyway. I'm raising it to the negative A6 power. A little less than 1. 0.909 million is 909,000. Copy and paste it down. It keeps getting smaller and smaller. This is the present value of the payment at time 3, which is the 4th payment. Present value of the 40th one at time 39 is about 0.0243 million. That'll be 24,300. Add those up. Cells C5 through C44 with equals SUM C5 colon C, what was it, 44? 44, we should get the same answer, 10.75695. Yes. Good, nice. Let's go back to doing it by hand though. Remember I said just a few minutes ago, what's really nice about this is actually just letting n go to infinity. Pretending our present value is an infinite series. I didn't put plus dot dot dots there at the end, but I could have. And when, by the way, here's an important point for me. When you do write down an infinite series with plus signs and no summation sign, you must write the plus dot dot dots. Otherwise, you will not get full credit when it's an infinite series. This is a finite one, so I don't need them after this point. But if it's an infinite one that goes on forever, I need to put the plus dot dot dots to signal to yourself, to me, the grader, that you are thinking about the infinite series. It's essential to be there. So let n go to infinity. We could think about it back here as we already have, and we get a over 1 minus x, because x to the n is going to go to 0. We also could think about it in terms of r. I happen to do that in the first section, so I'll do it with you as well. If, again, r is bigger than 0, so 1 plus r is bigger than 1, and x equals 1 over 1 plus r is less than 1, it also happens to be positive. Then as n goes to infinity, it's going to converge. Then x to the n, which is 1 over 1 plus r to the n, goes to 0 as n goes to infinity. So what you could say is when n is large, the present value of the annuity that will stop after you die would be approximately the limit of this as n goes to infinity. Let me just say the present value is going to approach 1 minus 0 over 1 minus 1 over 1 plus r. Because that thing right there goes to 0 where I'm pointing. And if I multiply the top and the bottom by 1 plus r, that simplifies to 1 plus r over r. This happens as n goes to infinity. And it's going to be also very close when n is fairly large. And by fairly large, I mean, say, 30, 40, 50, 60, etc. These are going to be pretty close together, the present value and this quantity. And this quantity doesn't depend on n. Hitting home my point that as n goes to infinity, things actually get simpler. That's the true value of infinite series, is that when you go to infinity, things actually get simpler. In many, many contexts, not just geometric series. They get simpler, often computationally. Sometimes the simplicity is more a conceptual simplicity in terms of ideas. I'm thinking in particular of Taylor series and representing things like sine and cosine in terms of infinite sums. Computationally, you might say it's more complicated to compute sine of x as an infinite sum, but conceptually, instead of approximating sine of x with a finite sum, thinking of it as an infinite sum in many situations is better. Not quite done. Let me also graph this as a function of r. Let's do it in Mathematica quick. Let's make a plot. Actually, I have two functions, 1 plus r over r, and the constant function 10. Why do you think I'm wanting to plot the constant function 10? Yeah, as a comparison with the lump sum. Don't forget about the lump sum at time 0. Its present value doesn't depend on r because the payment is at time 0. Its present value is $10 million. For r, say from 0 to some pretty small numbers, because we're talking about interest rates here, say 0.2 or something. And what do we see? Obviously, the horizontal line is at 10. The curve, the blue curve, is this function 1 plus r over r. what do these outputs represent? They represent present values. And so what this graph is telling you is that when the interest rate is less than around 11%, the present value of the annuity, at least if you live a long time, is higher than the present value of the lump sum. So this helps you make a decision. If you think interest rates are going to be less than 11% and you think you're going to live a long time, go with the annuity. On the flip side, if interest rates are really high, bigger than 11%, and you're confident in that, and you're also confident you're going to live a long time, well, there, I guess the length of time you live wouldn't matter because it's still better just to go with the lump sum. Go with the one with the higher present value. Okay, so very practical math there.